See, a nucleophile is a group which carries a lone pair and attacks on a delta positive charge and not on H plus. This is very important. If it is attacking on H plus, then we call it as a base and not a nucleophile. Okay,
Okay.
right. That is the first distinction. So, a strength of a nucleophile is called as the nucleophilicity. Like a base strength is called basicity, we call the strength of nucleophile as a nucleophilicity. If you're going from left to right in the periodic table, nucleophile always follow the basic order as well. For instance, if you see for hydrates left to right due to electronegative differences, HF will become stronger acidic acid compared to water, compared to ammonia or methane. Correct? So
Hmm.
left to right, acidic strength is increasing. Hmm? But what is happening to the conjugate base? Because this is the weakest of the acid, its conjugate base will be the strongest. So CH3 minus will be the strongest base, then NH2 minus, OH minus, and F minus.
Hmm.
Since this is the basic character, the nucleophilic character follows the same. Done, beta. So this is the nucleophilic character what you have. Got it?
Okay.
Next, if you go down the group, okay, from HF towards HI, what's happening? Bond dissociation energy is decreasing. So if bond dissociation energy decreases, breaking HI bond is very easy. That makes it a stronger acid. Okay. Since HI is a stronger acid, I minus is a weakest base. And HF is a weak acid, so makes it F minus as a strong base. And
Hmm.
this is a basic character which is followed. But nucleophilicity, whether it follows or not, depends upon what solvent you are using. If the chemical reaction is being done in a polar aprotic solvent or
Hmm.
non-polar solvent, then nucleophilicity will follow the basic order, which means F minus is a strong nucleophile, then Cl minus, Br minus, and I minus. Okay, but
Okay.
if nucleophilicity is observed in a polar protic solvent, PPS, polar protic solvent, in that case, it is inversely proportional to basic nature. Okay, it is inversely proportional to basic nature. That means if the basic nature is more, the nucleophilic strength is less. Therefore, I minus is a very, very good nucleophile compared to Br minus, then Cl minus, and the least one is F minus.
Hmm.
Got it? So I have written that here. You can see nucleophilic order in PPS, polar protic solvent, in PAS or NP. Okay.
Yes,
Same way
sir.
in PPS, this is for group 16, this is for group 17. All right. Please check. Did you get this or no? What are polar protic solvent, aprotic solvent? Please check the uh, list as
Hmm.
well. Done?
Yes, sir. Done.
Right.
So can I please use the washroom and come?
Yeah, sure, beta. Go.
Sir?
Have it up.
Yes, sir.
Check. These are the cases of nucleophilic strength. Okay. And these are not solvent based. Irrespective of the solvent, this is the order which you'll have. For example, if you're comparing CH3O minus and PHO minus, okay, in which O minus is localized electrons. There is no resonance here, but this phenoxide will have oxygen which would show resonance, right? So that means this CH3O minus would have more nucleophilic strength as compared to that of PHO minus, then RCO minus, then RSO3H minus, because these two also have resonance, and this is coming from their acidic strength. If you do recall, sulfonic acid, that is RSO3H, is the more acidic one compared to carboxylic acid, compared to phenols, compared to alcohols. So alcohols are weakest acids, so that makes it the strongest basis. Clear? So this would be the strongest base here. Understood? Right.
Yes, sir.
Next, steric factor. Check out the steric factor here. Nucleophile is inversely proportional to steric factor or steric hindrance. It is also inversely proportional to the basic nature. So you can see CH3O minus, C2H5O minus, and alkoxide here and tert butoxide here. If you compare these, tert butoxide has the more basic nature. Correct? It has a more basic nature. Then if you compare the nucleophilic strength here, so you can see alkoxide, methoxide, because the crowding makes a very important factor for nucleophilic strength. So least the crowding, better is the nucleophilic strength. So methoxide, ethoxide, isopropoxide, and tert butoxide. That will be the order of nucleophilic strength. Done?
Yes, sir.
Next, leaving group. The part of the substrate that leaves the substrate is called as the leaving group. For example, CH3Cl. The Cl part is the one which is leaving and creating a carbocation or maybe delta positive charge. It may not be completely creating a carbocation, yet it is the delta positive charge which we are getting it. Clear? So these kind of groups which are giving delta positive charge or complete positive charge, the group which is leaving is called as leaving group. Usually, to check out whether it is a good leaving group or not, we assess only one criteria, that is what kind of a base it is. If it is weaker the base, better it is a leaving group. Okay, so you notice out of these four, fluorine, chlorine, bromine, and iodine, iodine is a excellent leaving group. Okay, because it is a very very weak base. Hi is a very strong acid that makes I minus as a very weak base, and very weak base is an excellent leaving group. Got it?
Yeah.
Apply the same logic here also. RSO3H is a very strong acid, correct? So that makes RSO3 minus as a very weak base, and very weak base makes it as an excellent leaving group. Done? Always try to relate this way. Clear, beta?
Yes, sir.
So again, RSO3 minus is a very best leaving group. ACO minus, phenoxide, CH3O minus. There are
Sir,
some.
I have.
Hmm.
So you said that HF is a weak acid, but when like in TV shows like Breaking Bad, they use that acid and it just like melts everything.
Not
And in
everything, only ceramic part. If you store in plastic, nothing will happen. HF is a very stable acid in plastic.
okay, but then I read this like I watched this documentary of this serial killer and he used
Mhm.
HF and it melted skin and all. So but
Skin
skin
will
is not.
melt, na beta. Skin will melt because skin, the pores which you have will have salt in it. Clear?
Oh,
The pores
okay.
which we have it will always have salt in it, and More importantly, HF, the minute you bring it to any aqueous form, okay,
Mm.
one important factor of HF is it gets hydrated very fast because fluorine has high delta negative charge. If you
Yeah.
add water, water will surround it more easily. It has high hydration energy. And due to hydration energy, some temporary energy is released out. Okay.
Ah,
That will help in breaking out the molecules. Okay.
okay, okay.
So HF is kind of different compared to others. Okay. Because it has different types of roles in different solvents. Got it?
Okay, all right.
Mm. So strength is primarily decided on the basis of how much H plus it is increasing. Correct? It is not
Mm.
based on reactivity. It is based on whether it is able to increase the H plus ion concentration or not. Hmm?
Oh, okay, okay.
Hmm. Clear? Right.
Yes, sir.
Let's see this now. Now, these are referred as very, very good leaving groups. Okay. OTF, OBr, ONS, OTS, carbon monoxide, and N2. See why it is. Suppose if I remove this N2, you get a carbocation and a very stable gas, N2 gas. So
Mm.
N2 is a very, very stable gas which can easily release. So that means if this kind of a compound is forming somewhere in the intermediate, you can always expect that N2 without any notice it will escape away and leaving
Mm.
behind no matter worst of the carbocations, it will still leave behind that group and go out as N2 group. Same happens with the carbon monoxide also. If this carbon monoxide part is attached to some alkyl group, it will easily say goodbye to it and go away as carbon monoxide gas. We don't
Mm.
require any push or external energy, nothing. वो अपने आप से चला
Mm.
जाए. Okay. Same is the case with OTS. This is a group called OTS. This is a group called, ONS. Clear?
Mm.
So this is nitro. This is called basically, this is toluene group and this is sulfonyl group, right? That's what is
Yeah.
called, O, which is oxygen. This is oxygen based, right? This is
Mm.
toluene sulfonyl group. So that's what is called tosyl chloride or tosyl group. This is simply
Mm.
tosyl group with oxygen. So that's why it is called OTS.
Okay.
And this is nitro toluene kind of a group. You call it as a nosyl. This is bromine with a group similar to toluene known as brosyl. This is a word is used. ONS, nosylate,
Mm.
brosylate, tosylate. Okay.
Okay.
OTS known as triflate. CF3. No, no, sorry. My mistake here. Let me rewrite that. CF3 SO3 minus. Okay, not CO minus. This is
Mm.
called triflate. Clear? So this is also very, very strong. OAC is moderate but a good leaving group as well. Okay.
Okay.
So now you can notice that these are all good leaving groups. They are not extremely great, unlike these cases, but all of them are good leaving groups. These are very, very poor leaving group. That means you cannot expect them to leave easily unless there is some very critical condition in the molecule. Got it? So that's why.
Okay.
Now, one thing is for sure, a good leaving group cannot be replacing a poor leaving group like OH minus. That means this
Mm.
reaction is not feasible wherein chlorine can go attack, remove OH minus. ठीक है बेटा?
Okay.
Why? Because OH minus is a very poor leaving group. Cl minus is relatively good leaving group.
Yeah.
Okay? Or you can simply compare their basic nature. Cl minus is a very weak base. OH minus is a strong base. Okay? Never in
Mm.
reactions you will get a strong base out of weak base. You can always get vice versa. You can always
Yeah.
create a weak base out of strong base, but the other way around is not possible. That's why you see if there is an OH minus to be attacked here, then I can gladly say that the Cl minus will be replaced by OH minus and Cl minus will come out as a leaving group. Okay.
Yes, sir.
But if I want to make this reaction happen somehow, the first one, what I'll do, instead of directly making Cl minus to react, first I'll make the alcohol to get protonated. On protonation, you will get this as OH2 plus now, correct? And OH2 plus is a very, very good leaving group compared to Cl minus now, because if you go back here, water is a very good leaving group because it's a very weak base compared to Cl minus. Weaker the base, better is a leaving group. So water is a better leaving group. So water now can be replaced with Cl minus, and this is a reaction that can happen now. Earlier I was trying to get the chlorination done, but it was not happening. But now the
Yeah.
same chlorination was done.
Mhm.
The other alternative is to make this OH as OTS group. You react with tosyl chloride. This Cl minus will take H plus and O minus will connect to TS. So that's how you will get OTS group. And OTS is an excellent leaving group. Now again, if at all I react with Cl minus, that Cl minus will replace OTS and convert that into ethyl chloride. Done?
Yes, sir.
Right. I hope the part is clear. The basic idea of leaving group is clear. Right. Now let
Yes,
us
sir.
learn about SN2 type of reactions. One second, let me put my charge in. One second. Right. Check. SN2 type of reactions. When will this happen? Check. SN2 is a single step reaction. Within one step, the entire reaction will be over. Second,
Yeah.
there is no carbocation here. There are no intermediates forming in this reaction. Simple terms. Check out this one, methyl chloride. When you react with OH minus, the OH minus will attack here. Cl minus will come out of that, and you'll get this as methanol with Cl minus. Okay. So you can see this. This is how it is. Cl is here. OH minus is attacking. Chlorine is leaving. Both should happen simultaneously. So that means this bond breaking, this bond making and this bond breaking should happen simultaneously. So it goes through a transition state wherein it will have, this is a trigonal plane with OH above and Cl below. So it is a trigonal bipyramidal intermediate. Clear?
Okay.
So it is a
Yes, sir.
not intermediate, transition state. Trigonal bipyramidal transition state. And now, what is the rate of SN2? It depends mainly on this steric factor. If these hydrogens are being replaced by some alkyl groups, then the attack of OH minus delays. It becomes slower. Clear? So lesser the bulky groups, instead of these bulky groups, if they have only hydrogens, then the attack will be at a faster rate. Clear? That's why you see SN2 reactions work like this. So it has to have a very low substitution on the chlorine. Same is the case here, same is the case here, and same is the case here.
Yeah.
Got it? This
Yes,
is
sir.
about rate of SN2. Okay. So if we have methyl chloride, methyl bromide, and methyl iodide, and you're comparing rate of SN2 here, then iodide will make a better SN2 because of better leaving group ability. Imon is a better leaving group. correct?
Yeah.
So this is based on leaving group ability. Based on leaving group ability. Next, what is the overall rate of SN2? See, SN2 would make an excellent choice if you have at beta there is a strong withdrawing group like keto group. So if you already have a C double bond O with chlorine on the alpha position, then removing this chlorine and attacking with another group becomes more easier. Okay, this you have to mug up the entire order, very important order. Okay,
Yes, sir.
so this is the first group, beta hydroxy, sorry, beta carbonyl halide. Next, if you have an alkyl halide which is connected to a lone pair carrying group like oxygen or a nitrogen, that is also an excellent choice for SN2, because as soon as you leave the chlorine, the oxygen's lone pair will support temporarily in the transition state. Hmm? Because while leaving, this carbon is going, it is gaining delta positive charge, correct? अब पता चला
Yeah.
यहाँ पर oxygen है, so that will immediately make a support to this carbon temporarily.
Mm.
Got it? So
Yes, sir.
that support helps in increasing the rate of the reaction. The support can come either in the form of a lone pair of oxygen or in the form of a pi bond of benzene. Okay? So first
Yes, sir.
lone pair is more preferable than benzene. So that's why first one, this is an exceptional case, very, very exceptional
Mm.
case. Then you will have this,
Lone
lone
pair.
pair carrying group. Then we have a benzyl group. Then we
Mm.
have an, least substituted group, which is methyl chloride. Between these two, there is always a tussle, like which one should we go for? Should we go for some pi bond support? Isn't that going to be more effective? Now, this is purely database. So it could have come here also, it could have come here also. But as per the
Mm.
database, it suggests that methyl chloride will have more rate compared to allyl chloride. This is allyl chloride. And then
Okay.
comes ethyl chloride, which is 1 degree, then 2
Mm.
degree, and last comes 3 degree. 3 degree पे usually reaction होता भी नहीं है SN2 के लिए. Correct?
Okay.
You can see these are the group which does not give SN2. Have you noticed
Mm.
something? If SN2 has to happen, that carbon which is carrying chlorine has to be sp3 hybridized. This is sp3, sp3, sp3,
Yeah.
this is sp3, this is sp3, sp3, and sp3 hybridized. So if it is not sp3, if it is a double bonded, which is sp2, which is sp2 here, these cases will definitely not give SN2. So double bonded chlorides or double bonded carbons with chloride, or double bonded or triple bonded carbons with chloride, they would not give a better reaction for SN2.
Mm.
But if you have, 3 degree chloride here, then also you will not make a much great reaction in this case. If the 3 degree on the bridge are the worst positions to make SN2, because SN2 is basically attacking from the back end. If you notice here, chlorine का orbital ऐसा है, उसका back orbital is this way. The back orbital is sigma star. Clear beta? So attack is
Okay.
happening on a sigma star orbital. So, but the
Mm.
sigma star orbital, if it is masked like this, you can see there is the bridge bond is like a hood here. Like this is like a hood here.
Yeah.
And
Yeah.
chlorine is coming towards you this way. And
Yeah.
within the hood lies, sorry, like this. Chlorine is going this way. And within the hood lies the sigma star orbital. Correct?
1 second. This is the hood, and chlorine
This
is
is like
coming
the
from
hood.
Age.
Yeah. Towards you, like this. है ना?
Okay. Okay.
Correct?
Yeah.
Now, what will be sigma star here, right? Backside.
1 second. 1 second. So we're talking about this particular structure, no?
We are talking about this one.
Yeah. So where's the pointy part?
Where, beta?
The top part.
Pointy part will be here on top, like this. See,
Okay.
this is a
Okay. ठीक है.
slab.
Yeah.
This is the hood
हाँ.
slab, like this. Correct?
हाँ.
This is the slab. And pointy one is up.
Okay.
like this, up.
हाँ.
Okay. And here is the chlorine part coming towards you.
Hmm.
So can you see that
Okay.
sigma star is there within the hood only, inside the hood. Okay,
Acha. Yes, yes. I got it. I got it.
correct. Hmm.
Yeah.
So this is where the sigma star will be, and that is inside the hood
Yeah.
now.
Hmm.
And attacking that position becomes difficult for a nucleophile. Hmm.
Yeah,
That's
because
why
it's different.
any kind of bridge compounds will never give SN2. 3-degree chlorides will not give.
Hmm.
sp2 carbons will not give. Okay, and
Yeah.
even a cyclopropyl group will not give, because this carbon is having a 60 degrees angle, है ना.
Hmm.
इसका मतलब the sigma star, I mean, this is how it will be. Chlorine is here, correct, and its sigma star
Right.
is here. This is where nucleophile has to attack. Remember, while nucleophile has to attack, what is the intermediate we have seen? This is how the intermediate should happen, right?
Yeah.
But in this intermediate, what is the bond angle? 120 degrees.
120.
So, लेकिन यहाँ पे कितना बॉन्ड एंगल मैक्सिमम मेंटेन कर सकता है? ओनली 60 डिग्रीज.
अच्छा.
So ये तो
Okay.
वो इंटरमीडिएट बनेगा ही नहीं. So there is no
हाँ.
point of making any SN2 on this one.
Yeah.
Although this is a very valid case, you have a proper sp3 carbon on a primary position.
Hmm.
Nucleophile should come and attack. But the problem is on the beta position. On the beta position, there is an extremely bulky group. So if on beta position you have a very, very bulky group, then also SN2 is usually hindered. SN2 mechanism is hindered. Okay. Any doubt here?
Yes, sir.
Shall we go ahead?
Yes, sir.
Next, check out. Attack of nucleophile from the back side, a chiral center will undergo inversion. See, if this is a chiral center, beta, and I have written it this way. Clear?
Hmm.
Now tell me, as soon as I remove this chlorine out, you will get OH group, correct? By SN2 mechanism. But if this was something like an R configured, I think I discussed with you how the absolute configuration works, right? When is it R, when is it S? We discussed that, right?
Hmm.
So imagine if this is R configured, after the reaction, it has to become S configured. Then, which we say that the inversion has happened. That means we are able to do it inversion.
Hmm.
Clear?
Yes, sir.
Right. So therefore, you can see R becoming S. That is about the inversion group here. Cl minus will leave. Now, this is about SN2 type of reaction. Any doubt with SN2?
No, sir.
Right. Now, let us talk about SN1 now. SN1 usually happens via multi-step. There is carbocation formation here. There is a rearrangement also happening. It goes exactly in the lines of even reaction, even mechanism.
Yeah.
Suppose if you have a bulky alkyl halide and you react in the presence of water, the water would attack here, chlorine will go, you will get an 3-degree alcohol. How does the mechanism take place? The first step is to remove this chlorine, gets a carbocation. So Cl minus is a good leaving group, it will leave and generates a carbocation. Once you get a carbocation, that's when the water will attack as a nucleophile to get this proton, to get this OH hydroxy group added, and H plus has been relieved. Okay. Here in the example, I took something where carbocation is directly forming as a stable one. But in case if the carbocation is first forming at an unstable position and then it has ability to get more stable position, you will do all that rearrangement. Hmm?
Yeah.
Then rate of stability of rate depends upon the stability of carbocation. It is inversely proportional to nucleophilic strength. Remember, water is a very, very weak nucleophile, right? Usually charged, usually if you have any neutral lone pair carrying groups, they are generally weak nucleophiles like
Hmm.
water, alcohol, acid, right? These are all methoxy group. These are all weak nucleophiles. Okay.
Okay.
So if the strength of the nucleophile is weak, it will always help the rate to go faster via SN1 mechanism. What is the rate of SN1? That means you remove iodide, bromide, chloride. If you compare, removing iodide is more easier. Okay. So therefore,
Okay.
RCl less than RBr less than Ri. Next. Now notice the rate of reaction. Here, if you have any oxygen carrying group on CH2Cl, just we have studied that for SN2 it is an excellent case. For SN1 also it is an excellent case. You remove this chlorine, gets a carbocation. That carbocation will be immediately stabilized by converting into its octet form. Correct? So it will complete the octet form here. Shana Klebuta.
Yes, sir.
Next. Remove this chlorine, you will get a carbocation here. So this will become CPM carbocation. That means this is how it is with CH2 plus. This is called CPM carbocation. Cyclopropyl methyl carbocation. Clear? CPM carbocations are also excellent carbocations because of its resonance, which is sigma based. This is how the resonating structures are formed for it. These are called sigma resonating structures. These three are the resonating structures. Got it? So
Yes, sir.
therefore, this is also very good case for carbocation formation. Next, removing this
Mm.
chlorine, getting a carbocation turns this group into aromatic group. So that's why chlorine, remove chlorine, get a positive charge here. The ring will become aromatic, correct? So this one, this one, this one. These are very, very good in terms of carbocations. Next,
Mm.
triphenyl chloride is also excellent for carbocation. Diphenyl, what is a dibenzyl carbon here. Then 3 degree, 2 degree, 1 degree. Got it?
Mm.
So this is the correct way of making a rate of reaction for SN1. Just like SN2, here also if you have any vinyl group, phenyl group, right? Or for this case, where if you get a positive charge, the ring will become anti-aromatic, correct? This will
Yeah.
become anti-aromatic. So neither this nor this are favorable in SN1. Bridged is anyhow not favorable. One case, its
Yeah.
sigma star is inside, so SN2 is not favorable. Second case, remove this chlorine, you get a positive charge. Positive charge on a bridge position is impossible. Okay, because you need to have this kind of group here, like this, with a positive charge here. Correct? A positive
Exactly.
charge is expected to maintain 120 degrees angle. Clear?
Yeah.
But it is not going to happen. Now, here it is an important case. SN1 is noticeable in cases where you have multiple carbons on this case here, like this. So here I cannot say SN1 is not happening. Here it is been observed. Reason being, if you remove this chlorine, gets a positive charge. Now this is still going to be slightly stable. Okay, because here it can sustain that ring strain. It can sustain the ring strain here. See the ring size 1, 2, 3, 4, 5, 6. So at this
Mm.
place, even if it gets a slightly, planarity, it can still sustain. So that's why this one is a definite case, and this one is a definitely not the case. Okay,
Because there's 5 carbons there.
5 carbon case. Okay,
Okay, so if it's like 5 or less in bridgehead,
5
then
or
it's
less
not.
bridge will never make any SN1, neither SN2. Actually, this will not
Yeah.
make SN2 for sure, correct? But just in the
Huh.
case of SN1, you can note there is a noticeable amount for this case.
Okay. All right.
Next, attack of nucleophile can happen from both sides. Racemic mixture is being formed, will be formed. Like
Yeah.
if you have chlorine here, I remove the chlorine here. OH had to be attached. So therefore, OH will come on this right hand side or the left hand side. It might be
Mm.
50-50% chances. So that is going to be racemic mixture.
Mm.
Got it? So now check it out. Next, alcohol, when you react with SOCl2, will become alkyl halide, which is RCl, and SO2 and HCl. This is the product which you will get. Okay. This reaction type is called SNI type of reaction here. Got it?
Okay.
Now, what is SNI? See, first, the lone pair present on alcohol is attacking the empty orbitals, empty d orbitals of sulfur, trying to remove the chlorine out. So you will get this product first. Okay. Once you get this product, internally, here there is oxygen connected to sulfur, then chlorine. This sulfur is on sp2 hybridization. So the chlorine will be on the same location. So now what happens is this chlorine will internally try to attack this carbon when oxygen is leaving, making into a double bond. So oxygen makes a double bond with sulfur, converts into SO2. This Cl minus will get connected on here, and HCl vapors are anyway gone earlier. Right? This is how the alkyl halide is been formed. Okay, beta.
Okay.
This type of mechanism is called SNI. Why, if this carbon has, let's say, because I have not written any configuration on this, let's say this carbon has R configured. And since where the OH is leaving from the same direction it is connecting to chlorine, the configuration is always retention. So if this is R, retention takes place and it will remain R only. This is about SNI type of reaction. Shana clear, beta? Right.
Yes, sir. Yes, sir.
Now, the same SNI as a special case, if you notice here, I have not written that, let me write. If I have any alkyl halide RCH2Cl and I treat that with SOCl2, but this time in the presence of pyridine, if I take it in the presence of pyridine here, then I will get this as instead of this H, I will write it as deuterium, okay, D. So I will get this as RCHD, right? This is OH. And this will become Cl plus SO2 plus SO2 plus pyridinium chloride, like this, with H and positive charge with Cl minus. Correct? Now, in this case, what happened is first the lone pair, lone pair attacked on sulfur, chlorine has relieved, it took H plus. That
Yeah.
HCl reacts with the pyridine. Pyridine is a base, so it will become pyridinium chloride. Okay, beta.
Okay.
Pyridinium chloride has a dissolved form of pyridinium salt and Cl minus. So Cl minus is an excellent nucleophile. So it will attack externally from backside to remove the sulfur group. So therefore, this is going via SN2 mechanism. Okay. And this is called as Darzin's reaction. Darzin's inversion reaction. So basically, if you make the same SOCl2 in the presence of pyridine, it is called Darzin's and the mechanism is SN2. Without pyridine, if it is simple ether, basic ether here, and not pyridine, then it is SNI reaction. Clear, beta?
Okay.
Right. Next one is SNNGP. NGP is a word that is being used to express that there is a neighboring group which is also participating in the reaction. Okay. Officially, it is called as an chimeric effect or assistance. An chimeric assistance or effect. Usually, this happens when there is a group present on third position of the carbon or third position from the main chain or fifth position from the main chain. If they have a lone pair carrying group, that would support to leave the group more easily. For example, if you notice, this is position 1 where the leaving group is present, then 2, and third position we have a sulfur, correct? So on the third position, this sulfur would attack on this first position, removing out this chlorine instantly before even the solvent approaches. Okay. And it will lead to this carbocation. It leads to this positive charge sulfur, plus Cl minus. And once you have a positive charge sulfur here, now the nucleophile, in this case it is water. Water can attack either on this position or on this position, does not matter because both the positions are same. So as it attacks here, the bond will break onto this side. So sulfur will regain its original structure. And on this position, now you have OH instead of chlorine. Done. This type of a support is called as unchimeric assistance. Okay. Now notice if this position was R configured, hai na? If this is R configured, sulfur has attacked Cl minus has gone. So what is the intermediate which is forming? See, this is how the intermediate has been formed. So we will have hydrogen here, deuterium here with a plus charge. Done, beta. Now this is where sorry, deuterium is also there only. These two are H2. This is, we have H and deuterium, and here we have two hydrogen and hydrogen, right? So this is carbon 1, 2, 3. So this is 1, 2 and 3. Okay? This is how it is. Now the nucleophile water will again attack here, remove this group. So have you noticed first initially it was R configured. Now as soon as the sulfur attacked, it has become now S configured. Now again when the water attacks here back and breaks this bond, breaks this sulfur bond. Again it is SN2 kind. Now this time this product will come to a retention and it will become S configured. Done? So what happened? Just like in SNI, there was a retention. Here also, there is a double SN2 reaction happening. One is internal SN2 reaction, one is external SN2 reaction. So because of that result, again there is a retention in the configuration. So R will remain overall R only. Sorry, this is R. Okay. So S will become R. Clear? R will remain R. So you can see there is a two SN2 reactions happening on the same carbon that leads to the retention of the group. Any doubt here?
No, sir. Got it.
Clear? Right. Last one is about SNTD. SNTD is when you have a reaction like RMGX attacking, this would become O minus. Okay, O minus bana. The O minus will again push it inside so that the chlorine can leave, again retaining back this double bond status. So if you are making an square planar sp2 carbon, it is a square planar, right? Sorry, trigonal planar. Trigonal planar sp2 carbon convert into an sp3 which is tetrahedral. This is tetrahedral structure, intermediate. And from the tetrahedral, it is pushing back to remove this chlorine and to get back what is its original form, which is sp2 and planar, trigonal planar. Correct?
Right.
Right. This type of mechanism where an sp2 carbon is converting into an sp3 intermediate, which is tetrahedral driven. That's why the reaction type is called SNTD. TD means tetrahedral driven. Okay. So through SNTD, you will get this final product, which is substitution again. Clear, beta?
Okay.
Done. So these are the mechanisms which you need to associate with this topic. Clear? So the briefing of the mechanism is okay, but we need to do a lot of solving on this. So you will get to know how the problem solvings are involved from SN1, SN2, SNI, and SNNGP and so. Okay, beta. Right. So next session